Alright, so the first thing we want to do is we want to prove these inequalities about uh, lowercase and uppercase m, and then lower sums and upper sums. So, uh, for any partition P, for any subrectangle S in P, for any x in this subrectangle, we have the infimum over all s of f of. So this is the infimum over all x and s of f of x, plus the infimum over all x and s of g of x is going to be less than or equal to f of x plus g of x. Because if you have a particular f of x, then the infimum over all f, or the infimum over all s of f is certainly going to be less than or equal to f of a particular point x, and likewise the infimum over all of s of g is going to be less than or equal to g at a particular point x. So that's why this inequality holds. And taking the infimum here over all x yields, well, what's going to happen to the left-hand side? Well, the left-hand side here is a constant. And so if we take the infimum over all x and s, it doesn't, the left-hand side doesn't change at all. So we still have the infimum over all s of f, which by definition is MSF. And then we also get MSG here. And then on the right-hand side, we take the infimum over all x and s of f of x plus g of x. That, by definition, is lowercase ms of f plus g. Likewise, if we look at supremums instead, what we have is, let's see, so it's going to be f of x plus g of x is going to be less than or equal to the supremum. Well, I'll just write it as capital MSF plus capital MSG. And then you can take the supremum over all x and s, and the left-hand side will become ms of f plus g, and the right-hand side, being a constant, won't change at all. So I guess this exercise is going to come down to knowing when we are allowed to take supremums and infimums over inequalities to get what we want. Because that's the main idea behind a lot of these integration problems. It's that if you have an inequality, typically if you have an inequality, you can take an infimum and the inequality will still hold. And so you've got to make same with supremums. And the main issue is making sure that you're taking the infimum and the supremum over the correct things to get the correct result. So we get this, and then summing, or multiplying by the volume of S, and summing over all S in this partition P yields, well, it's not going to change any of the inequalities. And so what we're going to have is, with the lowercase m's, you multiply the left-hand side by Vs, and you get MSF times Vs plus MSG times Vs. And then when you sum over all P, you're going to get, and you separate you factor out the MSF, you factor out the V of S, and then you get two separate sums, and one of the sums will be L of FP, the other sum will be L of GP. And the right-hand side, of course, will be L of F plus GP. And then we do similar thing to the upper sums, and we get UF plus GP is less than or equal to UFP plus F plus UGP. And that's part A. Okay, so we've done that, and now we're moving on to part B. And so part B, I did it before, and I think I did a lot more work than I needed to. And we are going to find out if I was being dumb then and did more work than I needed to, or if I am being dumb now and am doing less work than I need to, or perhaps I could be dumb in both scenarios. But in any case, this, I don't know, math is hard, so it happens. But I've looked over this argument and I can't see any issues with it. Say, okay, so given any epsilon greater than 0, since L of Fp will certainly less than or equal to the supremum over all L of Fp, which is equal to the integral over A of f, and we know that this equality holds because f is integrable. Because this holds, there is some p such that some partition fine enough such that if we take the integral over A of f and we subtract L f p, it's going to be strictly less than epsilon over 2. And that's because the fact that this supremum of LFP is equal to the integral over A of f means that given any epsilon neighborhood, we can find a particular partition P which will force L of Fp to be within epsilon of the integral over A of f. And since this particular LFP must be less than or equal to the integral over A of f, the signs work out in this way, that the integral of f minus LFP will be strictly less than epsilon, rather than L of Fp minus the integral of f being less than epsilon over 2. The signs work in this way since the integral is always going to be greater than the lower sum. Okay, so by this logic, choose a common refinement P such that we need to satisfy 4 things. The integral over all A of f minus L of Fp is less than epsilon over 2. The integral over all of A of g minus epsilon over 2 No, this can't be right. What did I do? Oh, of course, yeah, I switched the order. Duh. Okay, so what we want is we want the epsilon to be on the same side as the integral. The thing that I did before with the integral of f minus L of f, that makes it very clear that the left side is a positive number. But of course we can rearrange it to look like this, and this is what we're going to be using. So we need this, and we need this, LGP. Of course, we're able to do this. Here, well, I'll summarize that at the end. We've also got U. Now for U, things are going to be a little different. We're going to have U of Fp less than the integral over A of f plus epsilon over 2, and U of Gp is less than the integral over A of g plus epsilon over 2. So of course, using the same logic as before, for each one of these inequalities separately, there exists an individual refinement P such that this holds. Now, one of the things that we talked about is that taking finer refinements will get you closer to the value of the integral. So what we can do is we can take these these four partitions that we get from satisfying these four inequalities and find a common refinement to all four of these partitions. And this common refinement will also make these inequalities hold, because it will get the upper sums and the lower sums even closer to the values of the respective integrals. Now, I say common refinements. I don't know if it was talked about a ton. It looks like it was at least mentioned in this section. But if you have two, for any two partitions P and P prime, there exists a partition P double prime, which is finer than both P and P prime. And this is a really important concept, because if you've got one refinement which does one thing and another refinement which does another thing, then oftentimes you can use common refinements to find a refinement that will do both things. And that's exactly what we're doing here. We want our refinement to do four separate things, and so we find four separate refinements which each individually do one of those things, and then a common refinement of all four of those refinements will do all four of those things that we want it to do. Okay, so then, and this is the part I'm pretty sure this works. Okay, so take the integral over a of f plus the integral over a of g, and we subtract epsilon. This is, of course, we can break the epsilon into epsilon over 2 and another epsilon over 2. Now, if we look at these things separately, the first two terms, by our choice of p, is going to be less than LFP. And the second thing is going to be less than LGP. And then we know from part A that LFP plus LGP is going to be less than or equal to L of F plus G P. And LF plus G of this particular partition will certainly be less than or equal to the supremum over all partitions of the lower sum. And this we know from the textbook is less than or equal to the infimum of U F plus G P. And that's because for any partitions P and P prime, the lower sum of any function f at P is going to be less than or equal to the upper sum of f at P prime. And so because these two partitions are independent of each other, you can take the supremum on the left-hand side and the infimum on the right-hand side independently, and the inequality will still hold. And so that's why this inequality holds. And of course, these two things here are the things that we want to prove are equal, and whose value is equal to the integral of f plus the integral of g. And assuming that these are equal, their value is what we define to be the integral of the function f plus g. Okay, now of course this infimum over all partitions P of u of f plus g P is going to be less than or equal to u of this particular partition P, the special one that we've chosen. And we know again from part A that this is less than or equal to u of f P plus u of g P. And now by our choice of P, we know that this is going to be strictly less than integral over a of f plus epsilon over 2 plus integral over a of g plus epsilon over 2, which is less than or equal, which is precisely the integral over a of f plus integral over a of g plus epsilon. And now we're good to go, because taking epsilon to 0 yields it tells us that f plus g is integrable. because if we take epsilon to 0, then this string of inequalities becomes equality. And so in particular, the supremum of L of f plus gp is equal to the infimum of u of f plus gp. And that equality is precisely what it means for a function to be integrable. So the function is integrable, and furthermore, the value, well, when we take epsilon to 0, we get precise equalities, and the left and right hand sides we get the integral of f plus the integral of g. F plus the integral over a of g. So we get the integrability of f plus g, and we also get the fact that we also get the formula, which is that the integral of f plus g is the integral of f plus the integral of g. We get everything at once here. So this is a really nice argument. I'm glad that what I did before was I proved that f plus g was integrable separately, and I thought that I needed to use that in this argument, but it looks like I don't, because you always know that the supremum of the lower sums is less than or equal to the infimum of the upper sums, and yeah, everything works out nicely. So yeah. So that's B, and then C is proving that if you have a constant, you can pull it out front. So let's just do that. C. For all C and R, and for any subset E of R, the infimum over all, I'll write it like this. The infimum over all elements E of the set E of C times E is equal to C times the infimum over all elements E of the set E of E. And likewise for supremums. Basically, for infimums and supremums of subsets of the real line, you can pull out constants. And you should be able to prove this, because basically, let's see here, what would you have to, so this might have been something that was proven already, because this could be a useful fact, which would show up in other places. But I'm trying to think, if you didn't know this, how would you go about proving it? Well, of course, if the infimum is obtained by a particular value, then it's obvious. If not, then you can look at a sequence of ENs and taking the limit of a sequence, taking a limit of a sequence and multiplying by a constant is the same as multiplying the sequence by a constant and then taking the limit. This is the basic idea. So I don't know how much detail is necessary for this fact. It could be possible that you might be expected in a class to provide more details on this, but I decided that it was standard enough of a fact that I wasn't going to write out the details. Okay, so knowing this, that essentially makes the rest of this just a whole bunch of you have to just go through the rest of the definition of the integral with this fact. So what this tells us is that C times MSF is equal to MSCF, because here the set S is just, so E is just a set S. No, E is the image of F. If you look at the values f of x for x and s, this just becomes a subset of the real line, and so you apply the fact from before to it. So this holds for lowercase and uppercase f. And so then you multiply by the volumes of these rectangles, and you sum over all of the rectangles, and so then you get C times LFP P equals L of CF P, and CUFP equals UCFP. So, if we look at the supremum of L CFP, then again, so first of all, we take out the C here, CLFP, and then again, we're taking a supremum of a constant times a set, and so you can pull that C out. This is C times the supremum of LFP, but we know that F is integrable, and so this is precisely C times the integral over A of F. And likewise, if you have the infimum of U CFP, then you pull the C out of the U, then you pull the C out of the infimum, and then you get C times integral over A of F. So CF is integrable, and the integral of CF equals C times the integral of F. And that's what we wanted to prove. Okay, so what do we do? Part A was proving that we just have some inequality, which would be useful for us later. Really, the only reason we needed part A was because it helped us in part B. And then parts B and C told us that integration is a linear function. So if you have a linear combination of functions, then the integral of the linear combination is a linear combination of the integrals. And that's a really important property. Of course, like we talk about, like the subject of linear algebra is talking about vector spaces in which linear functions. So anytime you have some operator which has linearity, there's a whole bunch of things you can conclude about it, and there's people study linear operators in general. So linearity is an important property of any operator, and integration is an operator, and as we can see here, it is linear. And so for this reason and for many other reasons, integration is really useful and it's really special. So yeah, the point of this exercise is that integration is linear, and even in the next maybe the next exercise, I don't think I've done that one yet, but in later exercises, you already go ahead and start using linearity, because it's really useful for giving you ways to deal with functions. If you have a function and you're like, I don't know how to integrate this function, but I know this function is a linear combination of functions that I know how to integrate, then you automatically know how to integrate the function, because you just take the linear combination of the integrals of the things that you know the integrals. So linearity is really useful, and integration has it, and so this makes a lot of things easy to integrate. And my laptop is running out of battery, which is so it's good that we are now done with the exercise so that I can charge it. And yeah, that's it.